Good morning, everybody. At least it's morning when I'm filming this. I don't know what time it is as you're watching it, but good morning. What I'm going to introduce here are the issues related to the thermodynamics of solution formation. I alluded to some of these in the intro video to solutions, and I'm going to introduce some of the ideas here again, and in the next video we're going to start to get into the nitty-gritty details. Essentially what we want to know is whether or not a solution can be made. So we know that things are spontaneous if the free energy change is negative. When it comes to making solutions, right, when it comes to taking a solid that might be in a bottle like this and adding it to a liquid that's in an Erlenmeyer like this, what do you think happens to the entropy? You take a solid and a liquid and you dissolve the solid into the liquid. Which way do you think the entropy is going to tend to go? Hopefully you said positive, right? The delta S of that system is going to be positive. And so that is pushing the delta G towards negative. So for solutions, the delta S is going to tend towards being positive. So that's helping. So then really what we have to focus our energies on, no pun intended, is enthalpy. We have to evaluate the heat change as we try to take a solid and dissolve it into water. And we're going to spend most of our time initially talking about solids and most of our time initially talking about salts, all right, pluses and minuses, charged species eventually dissolving in water. And I showed you a demonstration of that in the first video. If you remember, the solid I took, it was this guy here. It's backwards for you because my camera's backwards, but it was ammonium nitrate. And you saw that that salt dissolved pretty quickly in the water. But thermodynamically speaking, enthalpically speaking, do you remember what happened in terms of the heat? The temperature on my thermometer that I was measuring that day, right? It went down, right? The solution got colder as that salt was dissolving in the water. So it was an endothermic reaction, right? A delta H that would be positive, right? So, excuse me. So what we want to try to understand is why taking something like ammonium nitrate, NH4NO3, gave an endothermic heat of solution, why it get cold to our touch and to the thermometer. By the way, where's the thermometer? Is the thermometer in the system or the surroundings? Remember that. We talked about that before, okay? So it got cold. So we want to try to understand why that might be. Why does ammonium nitrate get cold when you dissolve it in water, right? Makes a nice ice pack. You ever sprain your ankle in PE class or playing a sport? All right, you get one of those instant ice packs, right? You kind of crunch it or punch it and you shake it up and it gets cold. That's essentially what's going on there's a salt that when it dissolves in water, it's going to make an endothermic solution, right? It turns out, on the flip side, if you take something like lithium chloride, and unfortunately we ran out of lithium chloride, so I can't sort of show this to you, but if you have lithium chloride, it turns out that solution's going to get hot as you make it. And it gets noticeably hot. Depending upon the amount you put in, it could actually begin to get uncomfortable to try to touch the Erlenmeyer. So that's an exothermic heat of solution, a delta H, that would be negative. So, again, why does lithium chloride get hot when it dissolves in water? They both readily dissolve in water, right? For entropy reasons, the solution wants to be made, and it turns out that for enthalpy reasons, both solutions will want to be made as well. So the question is, why do some salts get hot? Why do some salts get cold when you put them in water? And more importantly, as scientists, can we come up with any sort of trends, any sort of rules of thumb that will help us make predictions about future solid-liquid combinations and whether or not they'll be ultimately exo or endothermic and whether or not they'll tend to want to form solutions? So that's what we're going to get into in the next video. We're going to start to get into the nitty-gritty details of this analysis. All right? I'll save the nitty-gritty details for the next video, and I'm going to warn you, when I show you the next video, the first slide is going to look very, very busy because I'm going to show you the whole picture initially, but we're only going to take chunks of that picture as we go through it. So it's probably going to take 2 or 3 videos to get through all of the information we want to try to digest when it comes to the thermodynamics of solutions. All right? Why do some get hot? Why does some get cold? We'll try to figure that out.